Hey guys, welcome back to Pop 'em Up Chem. And in this video, we're going to be revisiting the idea of isomerism, which we looked at right at the beginning of the unit. We're going to be building on those ideas and looking at geometric isomerism. So we're going to go through what geometric isomerism is. We're going to go through two different naming structures and how you can apply them, as well as some of the implications of this as well. But as always, question for you to get started on, so just pause the video to have a go at that one. Okay, so hopefully you should have recognized that we have an amide. Now, if we have an amide group, then we know we're going to have the nitrogen and the C double bond O group in the middle. Now, D, C, and A do not even contain nitrogen, so based just on that alone, we know that the answer must be B. Earlier in the unit, we looked at structural isomerism, and now we're going to look at stereoisomerism. Remember, stereo in chemistry relates to the space that a molecule is taking up, just like in music, it represents the idea of bringing
space and a 3D sound, left to right.
So what do we mean when we say geometrical isomerism? Geometric isomerism refers to a type of isomerism which is based around the rotation of bonds. When we can't have rotation around a bond and there are different groups attached to the carbon that makes a bond, then in real space, it matters which position any group might be in because it cannot rotate freely around the bond. We can see this at play around a double bond if we have the two CH3 groups here. Because we cannot rotate around the carbon double bond, it matters if the CH3 is on the same or the opposite side to the carbon bond to the CH3 on the other side. We can also see this when we have ring structures, because rings also stop that rotation around a double bond, even though the bond is still a single bond. If we compare this ring structure with a corresponding straight chain, we could see that we could rotate the single bond so we wouldn't have alternative conformations. But in this ring structure, we're unable to do that because the conformation is locked due to the ring, and therefore it does matter which conformation the hydrogen and the CH3 group are in compared to on the adjacent carbon. We can use the cis-trans nomenclature to be able to differentiate between molecules that show this type of isomerism. We can draw these molecules in two ways. As I have on the left here, we have the substituent groups. The CH3 groups are on opposite sides of the double bond, and on the right I've drawn a conformation in which they are on the same side of the double bond. On the left we have what we call the trans isomer. A trans isomer is one in which the substituent groups, as in not the hydrogen, are on opposite sides of this double bond. If we draw an imaginary line down this double bond, you'll see that the groups are on opposite sides of this line. On the molecule on the right, they are on the same side of that line. We call that type of isomerism cis isomerism. In cis isomerism, we have the substituent groups, that's the non-hydrogen groups, on the same side of this line going through the double bond. Time for a little bit of practice then. First question, draw trans hex 3ene. Pause the video. Pop 'em up! So you can go about drawing this in two ways. One, the kind of straight chain way where you put your double bond in and then you recognize that trans is on opposite sides. So you can draw in the kind of three-dimensional representation in the bottom right here, or you can just draw it as a straight chain. Now you need to remember that when you're drawing it as a straight chain, you need to indicate that you understand which side of the double bond they're on. The easiest way to do that is to rotate the hydrogens around. That straight chain represents the exact same thing as drawing the C2H5 up here and the CH3 down in the bottom. Okay, have a go at hex 3ene then. Pause the video to have a go at that. Pop them up. So hopefully you were able to use what we just did in the previous question. You draw your 6 carbon chain with your alkene on the 3rd. Now it's trans, so you need to indicate the switching of the groups around that double bond, or you could have drawn it with this projection that gives the bond angles. Either way is fine. There are some problems with the cis and trans nomenclature in that it's a little reductive. If we don't have any hydrogens like in this molecule here, it can be difficult to see which one we have. And you may go, well, this is obvious. I've got a trans, they're the same on opposite sides. However, it gets a little bit more complicated if we have 4 different groups. Like here, if I replace bromine and iodine and put those in the molecule, what are we going to do in this situation where we have 4 different groups then? Well, there's actually been the development of a second nomenclature system called EZ. Now it's important to recognize that E and Z isomerism encompasses all of cis and trans, so EZ can be used for all molecules with a double bond, whereas the cis trans only with hydrogen groups. So E stands for entgegen, which is a German word that means opposite or in opposition to, and Z stands for zusammen, which again is another German word that means together. So just by their meaning, we can see how they would roughly correspond to cis and trans. Entgegen is going to be the trans isomer and zusammen is going to be the cis isomer. However, that's not the whole story. If we still don't have any hydrogens, we're going to need a way to decide a priority, if you like. Which group are we going to pick over another group when we're prioritizing and deciding if something is E or Z? Luckily, the priority system at its core is very simple. The priority is given to the atom connecting to the carbon with the highest relative atomic mass. The larger the atomic mass, the more priority given. If we look at these 2 examples, we're going to make our imaginary line across the double bond and then evaluate each side comparatively. So we're going to compare bromine and fluorine, of course bromine having the larger atomic mass, and then we're going to do the same on the other side, in this case chlorine having the higher atomic mass than hydrogen. So we can see here that the high priority groups are on the same side, so we're going to have a Z zusammen isomer in this case. However, we could also call it cis as it's got a hydrogen. Now, looking at the molecule on the right hand side, we see that the hydrogen and chlorine have swapped, so the priority on the right hand side have swapped, so it goes across the double bond. Now, if the high priority are on the opposite side, then we're going to have the E or the trans isomer. Let's do some examples to have a look at some of the details of this system. In this molecule, we can see on the left-hand side we have bromine and hydrogen. It's quite clear that bromine is going to be our priority group on that side. However, on this side, and this is where a lot of people make mistakes initially, is they see that the overall atomic mass of this group on the top, the C2H5, is larger, so they give that the priority. However, we're not going on the total atomic mass, we're going on an atom by atom basis. So we're going to go 1 atom out from the carbon, and then we're only comparing the carbon to the chlorine. The chlorine, of course, having a higher atomic mass. So it's important we only go out 1 atom at a time to be able to evaluate our priority. We're not doing the whole group. We go 1 atom at a time. So that means in this case, we of course have the E isomer because the priority groups are on the opposite sides of the double bond. So a common problem is what happens if we have the same atom on both sides? Well, we can solve this again by following the same rules. What we're going to do is we're going to divide the double bond and then, as I said before, go out 1 atom at a time. Now, when we go out 1 atom on the carbon on the left, we find the first atom we hit is the same. It's carbon on both sides. So to differentiate, we're going to go out one more atom and see what we get. Once again, we're left with a carbon and another carbon. So we're going to continue this process as we might expect. It's carbon once again. However, there is a slight difference this time. In the group on the bottom, the carbon is attached to one other carbon directly. When we have this, we kind of consider it as it being bonded to two carbons, and so we count that as 2 times the carbon for the priority, and so therefore the bottom group takes priority in this case. We have a similar problem on the groups on the right hand side. We go out one atom and we find it's carbon versus carbon, and another atom, and the problem is solved. Slightly more quickly this time, we have a carbon versus a chlorine. So the bottom group, again in this case, takes priority. This means we could call this the Z isomer. This rule about counting twice when it's bonding twice also counts for when we have double bonds. Take, for example, if we were counting outwards from the top, we would count 1 oxygen, whereas if we count on this bottom carbonyl group, we would count O times 2. So a double bond counts for 2, just as 2 single bonds would. Let's do one question on this before we move on to how this affects the properties of these molecules. Okay, so is this molecule E or Z? Pause the video to have a go at that. Pop 'em up! Following the same rules we just went through, on the left hand side we go out 1 and we get carbon, and then we go out again, we only get hydrogen versus carbon, so the bottom group takes priority. On the right hand side we go out 1, we get carbon. We go out 1, we get oxygen in both, but we have the double bond on the bottom, so we have it times 2, so we get the bottom group taking priority and therefore our Z isomer. There are 2 physical properties that this can affect, that's boiling point and melting point, and they're affected in 2 different ways, but fundamentally they're both operating on the intermolecular forces. One is packing and the other one is polarity. So packing is just like what it sounds, it's how close really the molecules can line up with each other. In the trans isomer, the molecules are much more likely to be aligned next to each other and allow London forces or other intermolecular forces to be able to build up and keep them together more. Thus, in effect, it means that in solid state, the intermolecular forces are higher in E or trans isomers, and therefore the melting point is higher in trans isomers. Considering polarity affects the boiling point, if we take this molecule here, one of which is polar because all of the electrons lie at one side and the other is non-polar because it's symmetrical, we have an overall dipole moment. An overall dipole moment means that in a liquid state, the polarity of the molecule will increase the intermolecular forces and make it harder for the compound to be boiled, and thus Z or cis molecules will have a higher boiling point. Now, we're not going to go into too much depth about how the chemical properties are affected because this varies a lot on the individual molecules, but they can be different when we have the E or Z isomers, especially when we consider longer chain molecules. If we take a look at the same molecule here in the different E and Z configurations, we have a carboxylic acid group at one end of the molecule, and at the other end of the molecule, we have another carboxylic acid. We have a dicarboxylic acid. Now, in the trans isomer, we get no reaction when we heat this. However, if we look at the cis, then the functional groups will be facing each other, and we're going to get an esterification of that bond, and that is where we can close the ring and actually form a ring-based structure, a furan ring in this case, which has very different chemical properties to that of the original dicarboxylic acid we had. So we can see huge variation in chemical properties here. Couple more questions to round us off then. So first question, which isomer of butene would you expect to have the higher melting point? Pause the video to have a go at that. Pop them up. So when we think about melting point, remember we're thinking about solid state packing and how closely these molecules can get to each other. And in butene for the E isomer, we can see that they stack very easily. They pack very well together. And so we're going to have a higher intermolecular force between these, which is going to mean it takes more energy to separate them. And therefore the E isomer is going to have the higher melting point. So next question, which isomer of 1-bromo-2-chloroethane would you expect to have a higher boiling point? Pause the video to have a go at that. Pop them up. So if we draw the molecule out in both configurations, both cis and trans, and then we kind of map where the electrons are going to be, we can see we've got heavily polar bonds in the chlorine carbon and bromine carbon bond, which means in the cis configuration, the Z isomer, we're going to have an asymmetry and an overall dipole moment, which means we're going to have larger intermolecular forces, which are going to make it harder to boil the cis or Z configuration, thus meaning the Z isomer has the larger boiling point. Okay, no practicals or worksheets for the end of this one. We're going to wait until we do optical isomerism next lesson so that you can start doing questions comparing both of those types of isomerism. Thanks again for joining me, guys. Don't forget, like, subscribe, share the channel, and as always, practice makes slightly better.